Swayam Prabha. Digital India. Educated India.
Hello, Namaste. I am back with the next set of lectures on data models, wherein we will be looking at first lecture is in terms of what do you mean by a vector data model. And when we look at the previous class that we have understood what do we mean by a data model. A data model is in terms of how do we represent a real world representation using rules into converting it to a data or a database, which actually can be queryable. It is a quantifiable or qualitative process. And now in order to represent that, we have different types of data. We have continuous data and we have a discrete data. So when I say continuous data, so you have a continuous set of values represented from a geographical location, whereas you have a discrete data which has discrete values, that is very specific, has a boundary, and it is represented over a geographical location. And this, to represent the continuous or a discrete data, we have fields and objects. Fields normally represent a continuous data and objects represents a discrete data. So when you are looking at this, the first kind of data model representation that you can find is nothing but a vector data model. In today's class, you would understand what do you mean by a vector data model, how it is represented, and what, for example, as I previously said, vector data model is normally represented your point, line and a polygon. What are the different ways of storing a point, line and a polygon? You have different data models, well known data models like spaghetti data model, and another one is a topological data model. So both of the data models can be used. Spaghetti is a very simple data model, whereas topology is a quite complex data model. So we will look at both of these data models. And the last way is how do you store your attribute data, how do you store the entire data that you have, and how do you retrieve it. So what are the different methods that you have to store, and if there are certain errors that should not be always performed in your database, that also we will look at in this particular class. So when we are looking at from the real world model to GIS data model, spatial data, as I said, is a numeric representation which analyzes, describes real world features in GIS. That is what is nothing but a spatial data. So when I say spatial data, you have a real world data with the geographic coordinates associated with, that is nothing but a spatial data. Now spatial data depicts a real world in basically two different data models. One is called an object based model, other one is called a field based model. Okay. When I say object model is has a different entities which are separable, whereas field data model is more of a continuous data. So GIS can organize reality through the data models. Okay. It can completely convert the real data to the digital data through the data models. When you look at all spatial data models, you can either put them into vector data model or into a raster data model, or both. So both of them are possible in the same data model, but these are in different layers. Okay. Now when we look at the vector data model, each real world objects are represented as a point, a line and a polygon. Let us take an example. Let us assume that we have a building. Okay. We have a building, and surrounding the building we have number of trees, and next to the trees is the driveway, or you have your roads that are actually there. So now if you have to represent this as a real world phenomena into your database, the first thing is you capture building, the edges of a building, that becomes a polygon because it is a closed loop of connecting line segments. Then you have lines. Okay. So lines that are represented in a form of a road, So, when you are actually routing a road in the database, you convert it normally as a line, though it can be very clearly represented based on a polygon, but normally when you are actually representing in the real world, in the data model, you represent most of these roads as a connecting line segments. Then you have points, for example, it may be identifying the particular building or number of trees around the building. So, all of these becomes a point. So, number of points connected will form lines, and each of the line segments that are connected forms areas. Areas are nothing but polygons, which are the representation of a vector data model. So, whenever someone asks you what is a vector data model, the first thing that you have to answer is it is a point, line and a polygon. So, always this has to be remembered. Okay. So, PLP is what you mean by a vector data model, the point, line and a polygon. So, always every data on the earth surface can be represented in a point, line and a polygon. So, remember, whenever you have a vector data model, you are representing the real world features in points, lines and a polygon, whichever data it is, whichever the real world phenomena it is. Okay. So, when you are looking at a vector data model as points, points is a fundamental object. You can represent any building, any corner of a road with a point. Point represents a discrete, please be careful here, discrete xy location. Okay. It is represented only by a discrete xy location, that is nothing but a points. A city may be a point, but when you go into looking at city boundary, it becomes a polygon. Okay. But city, for example, if you see, there are number of cities that have been represented here, tier 1 and tier 2 cities. Okay. Bangalore is a point, Tumkur is a point, Mysore is a point, Vellore is a point. Okay. But if you are representing the connection between Bangalore and Mysore, then it becomes a line, number of line segments, and if you are representing a boundary of Bangalore, then it becomes a polygon. Okay. So, now we understood what do you mean by points. Point is just an xy coordinate. Okay. But when you have line or a polyline is connected by sequence of points, if there are number of points that are connected as shown here, you have a node, you have a vertex, you have a vertex, number of vertexes, and finally you end with a node. This becomes a line. Okay. So, now where each endpoints are usually called as nodes, not the end. If you have one line segment here and then you have a connected, then this becomes a vertex and not as a node. Where it ends, it becomes a node. Okay. So, and the intermediate values are called as vertex, or number of values are called vertices. If we know that the start and the node coordinates of each line or a polygon or a polyline, we can compute the length of a polyline. So, which means length of a road. If you want to compute, then you should know what is a starting point, two nodes, that is the start node and the end node. Then lines are used to represent features that are more linear in nature. For example, it may be a river, it may be stream, rail, road, all of these features. So, any features that has number of points that are connecting in a certain fashion from a start node to the end node, then it becomes a feature of a line. And when we look at the third kind of representation, it is nothing but a polygons. If you see this this map, this is representing a number of lakes in the city of Bangalore. Okay. So, when you see, this is nothing but a blue color is representing lakes. So, when I say polygon or areas or surfaces, this is defined by a closed set of lines or sometimes called as polylines. Okay. So, you have, if you see this image here down, so you have this as a line, okay, second line, third line. So, these are nodes, okay, not the vertices, these are nodes, node 1 and node 2. There is a start node and end node for this line, this is a start node and end node for this line, there is a start node and end node for this line, start node and end node for this line, and start node and end node for this line, finally reaching the same start node of the first line. So, this becomes a completely a polygon. Okay. So, normally in a line, the start node and end node are different, whereas in a polygon the end node is nothing but a start node always. Okay. Polygons identified as closed set of lines are used to define features such as water body, lake, rock type, land use, administrative boundaries, all of these are represented by a polygons. This example which I have given here is a set of lakes in south east of Bangalore, where you can see these are number of lakes that we have extracted from a map source. Okay. So, then when we look at the vector data model, all vector elements are represented as using continuous geometry, that is point represents a position, line a length, and a polygon an area. So, when someone says find out the length, then you have to look at the number of line segments that are there. If you are computing the same area, so look at the entire loop of a polygon and look at the area. If you are looking at a point, then it is only a point. If for example, if I have to give you the location of this particular building, then I will just say the centroid of this particular building, the centroid point of this particular building, which represents this particular building's geographic location. Okay. So, that is how in a vector data model it is represented. Point is nothing but a position, line is a length, and polygon is an area. That is what I am representing it here. If there is a lake here, it is representing a point. Okay. When there is a line, it is representing the connected line segments and is representing length, and if it is a building, a point here, or even these points represent the position of that particular place, the geographic coordinates. Okay. If you look at your database, if you have a point, line and a polygon, if you give an ID as 1, then attributes as a and b, then the coordinates is 1 comma 1. Okay, because that point's geographic location has a single coordinates. But when you look at line, so if for example, if I have given it as a unique ID is 10 and attributes as c and d, I have just given a random attributes, and when you look at its coordinates, you will have a number of strings. Okay, this is a starting node and this is an ending node. Okay. So, when you have an area, let us say I have given the its unique ID as 100. So, it is a closed polygon, it will have several number of coordinate values. So, this is a starting node. Okay, and this is again another node, but the end node will be the same as a starting node, it is a closed polygon. Okay. So, this is how a vector data model is represented. I have not in the area part, I have not represented the end node. So, end node would be the same as a starting node. So, please keep that in mind. Okay. So, when in a vector data model, as I said, objects are defined by their xy coordinates in a planar coordinate form. Okay. When you look at the precision of coordinates virtually are infinite, okay, but are quite machine dependent. So, it is dependent on how you represent it, how you actually work on it. However, when you look at the accuracy, most often is quite limited. So, this whatever when you look at the vector data model, you have the accuracy which is quite limited, but the precision denotes the degree of agreement between the several measurement of quantity. So, it is not though we say it is not precise, but the precision is dependent on what you are actually measuring on the ground to the database. Then accuracy denotes the closeness of measurements of its true values, but it is always quite limited in terms of understanding. Okay. So, when you look at the vector data models, this can be structured and many different ways of storing geometrical information. You have two types of vector data model. One is spaghetti model. Spaghetti model is quite simpler model, it is very simple model in terms of representation, whereas topological model is a quite complex model. The way the data has to be represented is extremely complex. So, difference between them is in the level of structure and organization of data, how the data is structured and how the data is organized. So, that is a difference between these two types of models. And when we look at the spaghetti model, the point is represented in a form of x y coordinate pair like your vector data. or in a form of a vector data. So, line is a series of xy coordinates as represented the way. So, there is no change in definition. Area is a series of xy coordinates with the first and the last coordinate being identical. This is nothing but a closed loop, it is the same definition. I would not again deal into that, but when you are looking at the point model, points and lines would be encoded in a similar way. There is no difference. There is no relationship between point, lines and areas when you are looking at a spaghetti model. So, if you have points here, these do not have any relationship between points or lines and a polygon. Okay, it is just representations. And when you are looking at a line, each line is considered as a single strand. Okay, for example, this is the entire line, this is your starting node is A, then you have you have vertices here, you have this line segment. So, all of these are nothing but a single strand. Okay, each of this strand in this model, for example, AD is a strand which I have represented here. It has a coordinates of 2, 5 and 4, 4. If you see, A is 2, 5 and D is 4, 4. You see here it is 4, yeah, it is 4, 4. Okay, so that is how you represent AD. Whereas when you look at AB, it is 2, 5, 2, 2. Okay, you see here the A is 2 representing 2 and 5. Okay, and whereas B is representing nothing but 2, 2 here. Okay, so each of these segments is considered as a single strand. It is a complex shape, but it is a single strand. Okay, there more and more strands of spaghetti can be added. These strands are called as nothing but a spaghetti. So, you have points are represented. Now, you have line segments, each line segment is a strand which is represented here. Now, let us go into polygon model. So, any polygon that lies adjacent to each other must be made up of at least 2 strands of spaghetti or 2 lines. Okay. Each polygon must be uniquely defined by its own set of xy coordinate pairs. Okay. Boundary cannot be shared by adjacent polygons. That is one rule that it has. Okay. This creates, if it shares, it creates a redundancy in data. For example, when I say A is a polygon here. Okay, it is bounded by 1, 4, 1, 6, 6, 6, 6, 4, 4, 4, 1, 4. Okay, if you look at this, this is 1, 2, 3, 4, 5 line segments. 1, 2, 3, 4, 5 line segments. Okay, so 6 line segments. Now, when you look at this 1, 2, 3, 4 line segment, 1, 4 is a starting point here. If you look at this, this is 1 point, 2, 3 and this is the line. Okay, so this is how the polygon model is built. Now, when you look at advantages of this particular model, it is simpler to understand and store. You do not have to use much of the computational capability also. Then you have standard graphic models, which are standard graphic manipulation techniques that can be used on a closed loop polygons. The major disadvantages here is the spatial relationships need to be determined for each analysis. It cannot, the connectivity and contiguity, otherwise it cannot be used in its own way. Then redundancy of data is there in the entire system. The data is quite redundant. Then you have preferred system for very low end system, because if you have a system where it is not computationally capable, then spaghetti data model is something that you have to look at. And very importantly is that the geographical information or the topological information is difficult to analyze in it, or it lacks a topological information basically, because everything is represented as point, line and polygons, and the entire thing is nothing but strands and spaghettis. So, but when we look at the topological model, it is characterized by inclusion of topological information. Whatever is a disadvantage there is an advantage here. the spatial relationship between adjacent features in a data set always exists, whereas when you look at the spaghetti model, you always used to compute the relationships between them, whereas here you know what is the relationship which exists all throughout the way you are storing. Then records xy coordinates of a spatial features and encodes spatial relationship between them. It is also called as arc node data model, because normally it is in the form of a line and a node. So, arc is nothing but a line, and node is nothing but an end point of a line, or a point where two or more line connects, that is nothing but a node. So, it is the model is called arc line or arc node, arc node kind of a model. So, topological model is also called as arc node model, whereas arc is nothing but a line, node is end point of a line. So, when we are looking at the topology, topology is a set of rules, okay, be specific here. Topology is a set of rules that model the relationship between the neighboring points, okay. So, in a spaghetti model, we are not worried about point, lines and a polygon. So, it is about points, it is about lines, it is about polygons. So, it is completely different, but here it is between neighboring points, lines and the polygons, okay. It is a relationship between neighboring lines and points, lines and a polygon, determines geometry sharing between them always, okay. Topology is also concerned with preserving spatial properties when the forms are bent, stretched or placed under similar geometrical transformations, which are not happening in the spaghetti model. Three basic topological principles you have to always look at is connectivity. How do you define connectivity? How do you define area? How do you define the contiguity? If you understand all of these three things, then topological data model representation is extremely important or easier, okay. When we look at the topological data model, for example, here if you are looking at this, okay, the first node 1 is a point that is represented between 1 and 4. If you look at this particular node, node 1 in these are connected by 1 and 4, whereas node 2 is about 4 and 4, it is connected by 4, okay. When you look at the, if you see this, it is 4 and 4, okay. When the node 3 is 6 and 4, okay, and when you look at the node 4, it is between 4 here and 1, that is why you represent a point. And when you are representing a polygon here, a polylines A, for example, if we are representing any of those polylines, it is represented in the form of 1, 4 and 5. This particular polygon is bounded by 1, 4 and 5. All of these three are different polylines, okay. So, similarly we represent the polygons. So, each of this line based on the line from where to where, okay. In the left of that particular polygon you have an outside polygon, you do not have any space. I mean, when I say outside polygon, it means to say that there is nothing in between them, and on the right you have a polygon which is named on it. So, that is how we read it. So, topology, this is for when you look at this, it is a point, this is when you look at it, it is line, and when you look at this, it is about a polygon. So, point, line and a polygon. So, always topological model has topological data inbuilt in it, that is the biggest advantage of considering a topological data. So, when you are looking at advantage, it stores spatial relationship explicitly, okay, which is not done in a spaghetti model. It allows rapid calculation, determination, analysis of spatial relationships, which is extremely important. Spatial analysis can be done without accessing coordinates. You do not need coordinates, but you can do spatial analysis, and always allows error detection. That is extremely important in terms of when you are representing a data model. More complex disadvantages, it has a very complex data structure. Topology needs to be re-established after each update. Preferred system for very high end system. If you have a very high end system, and it is very highly preferred, okay. So, we are coming to the last part of this particular lecture. So, we have understood how are different types of data models, the vector data models, the spaghetti and the topological data model. Now, we will look at how do we store an attribute data. So, when the attribute data are normally stored separately from the coordinate data or in the same form, but the coordinate information is in a different columns, whereas attribute data is in a different column. So, when you are looking at feature identifier points to an attribute table, whenever you look at a feature, it gives you an attribute table, point attribute table, line or an arc attribute table and a polygon attribute table. So, each of these would have a separate attribute table connected to it. Okay. Similarly, we can define points or line or attribute tables if the spatial features are, for example, if it is a village, road, etc., then you can define the attribute table in this way. For example, let us say this is a polygon here, okay, this is another polygon, right, this is the third polygon, okay. I am representing area of this particular polygons here, the population here and the TFR. So, this has nothing but my attribute information, okay. So, the same ID will have the xy location of this particular polygon, where this is xy, this xy, this xy, this xy and finally this and this. So, that will give me the entire information about that polygon. So, you have geographical information also, you have attribute information also. The very important point of converting into database is to avoid redundancy. So, when you are storing for example, this data, this is about a province and the district data in the same table is quite inefficient. Why? Because province data need to be repeated for each district, right. So, if you have number of district, for example, here if you look at, you have the same province that is repeated for all of these districts. So, this becomes redundant, the population becomes redundant, but if you are representing something like this, so you have a unique ID that is represented here, you have a district that is represented here, you have a population, then you have a province. Now, this becomes more efficient database in terms of if you are trying to put it as a relational database. So, you will say that each and every ID has a particular relation that is attributed to it. So, you build a relational database and you represent the province like this. So, that becomes a relational database which is actually relating all your attribute data to your ID. So, redundancy is the one that you have to remove from your database. Now, if you ask me how do I actually remove the entire redundancy? Now, what I have done basically here is I have given province in a different database. If you have seen here, Raipur and T Nagar is represented here, instead of representing it in the main database, I have put it here. So, when I connect this with relations, it becomes the same database. So, you only thing is that it is stored separately, so that it is not in the same database, you do not repeat it in the same database. So, now if you ask me why and how you actually have different I mean how do you remove this redundancy, then it is how you do a normalization. So, when we look at different databases, different ways of representing a database, I will speak about normalization of a database, how different normalization you have, first normalization, second step normalization. So, we look at first form, second form, third form, etc. when we are looking at the database, but as of now it can be done using normalization. Okay. So, normally a relational database design provides the best storage efficiency. I will tell you what do you mean by relational database. Now, you now you have object oriented databases, etc. So, we will look at all of these databases and when we come to the database point, but as of now we have to remove redundancy. So, you need to have a normalization for your data. Okay. So, that is what you should remember. Then when you are storing attribute data, at whenever you have any data, it is attribute data that has to be stored. So, always just storing a geographic coordinate will not give you any output. When you have attribute information added to it, then it gives added value to that database. Okay. for example, in socioeconomic GIS applications, attribute data component is often a very large component in a database. If you don't have an attribute data, then that particular thing is not even called a database. It can be just a geographic base. Okay, for example, few provinces, hundreds of variables. So huge of any socioeconomic surveys, any physical survey, etc., will have a huge amount of attribute data. Without attribute data, your database has no value. Okay, so that's what I wanted to speak about the subject in this class. We have looked at what is a vector data model. It's a point, line, and a polygon. Basically a spaghetti we have data model we have looked at. So each point is represented as its own, and each of the point has a different, each of the line has different strands that is represented in a form of a coordinates. Then you have polygons. Each of the polygons are represented by different strands that are connected together. Each of these strands together from a starting node to the end node forms nothing but a entire data model of a spaghetti. When you look at topological data model, it is nothing but a arc node data model. Arc is nothing but a line, node is nothing but a point that is connecting each of these line segments, or is the end start and the end point in a polygon model. Then you have storing attributes data. How do you store an attribute data? I spoke about redundancy. You can always remove redundant data and make it another database where whenever it is required, it just populates into your sheet wherever you want to do the analysis. Then I also spoke about different how do you actually look at attributes data, how do you look at different databases, how do you actually remove redundancy. The main form of removing redundancy is using normalization form. You have different normalization form which we will discuss. So as of now, this is what we had to discuss for today. In the next session, we would look at different raster data models. So I would only speak about one kind of raster data models, so that's called as quad tree data model. So the rest probably I'll leave it out for you to explore. Okay, thank you very much. Let's meet in the next class.